here is analyze the nodes in this thing. Okay, so down here on the bottom, all of these sources are connected to the same node. This would be considered probably a node. This is a junction up here. So when it's a junction with three things connected to it, no sources, we probably got to write an equation for that one. We consider this a node here, and we consider this a node. So, one, two, three, four, five nodes at least in that one. Okay, so then you got to think about, okay, which ones of those do I have to write equations for? Okay, so one of the things about this is that our source is connected to here. Now this here is all at the same potential. That's the one we should make into the reference node. Okay, so there's our reference node. Now, are there any places with respect to that reference node where the voltage is known? Well, yes. The voltage here, this is the voltage rise going up here. The voltage here is 6 volts above the reference. Remember, the reference, we're considering that to be 0 volts. So the voltage here is plus 6. Okay, likewise for each node that has the other end of a source connected to it. So right here, the voltage or the potential is 10 volts. Why? This is a rise going up there, 10 volts above 0, 10 volts. Now, look at this one. The polarity on this, this is a voltage drop. So what did that tell you? The voltage right here is 12 volts below 0, negative 12 volts there. Okay, so, of the nodes there, I got the voltage at 3 of them. The other one I call a reference node. Well, I think I might have said there was 6 nodes, 5, right? So this one here, I don't know the voltage up there. I gotta write an equation for that one. A node voltage equation. Call it A. So, at node A, I have to define the currents there. And in the solution that I posted, I think I said the currents were entering, but I wrote my equations as if they're leaving, because we said that what? Our currents should be leaving. And so, should be leaving, right? So, he goes through R1, let's call him I1, he's leaving. This one goes through R2, let's call him I2, he's leaving. This one down here, now, what are we going to call that one? I called it I3 because I had it leaving, or I should have had it leading. And so forget the fact that that's the one we're trying to find that's labeled IX for now, right? We'll worry about that later. So we got 3 of the currents leaving. The sum of the currents that enter equals the sum of the currents that leave. I1 plus I2 plus I3 is equal to 0. So I1, in terms of Ohm's law, is the voltage drop divided by the resistance. The voltage drop is the difference in potential on both sides of the resistor. A resistor, a current, goes from a place of high potential to a place of low potential. So in giving this current a direction, right to left, leaving node A, we're saying that the voltage on the node A side is higher than negative 12. So the potential, or the difference across it then, is for I1, it is VA, subtract the voltage on the other side, which is negative 12, divided by the resistance of 100. Okay, plus I2. I2 is leaving. The voltage across it is VA, subtract plus 6, divided by R, 60. Plus the voltage, now it's I3. Remember, I3 flows from a place of high potential to a place of low potential. So the voltage across it, VA, minus 10, divided by R, 40. And that sum is equal to 0. Okay, let's simplify that now. We've got one unknown, and so we have VA plus 12 divided by 100 plus VA minus 6 over 60 plus VA minus 10 divided by 40 is equal to 0. Now, Mr. Wade tells his class to multiply by the biggest number in the denominators, but multiplying this by 100 I don't think gets rid of all the fractions, because neither 100 is not divisible by 60 or 40. And so the lowest common multiple is what you're supposed to use, and it is in this case 600. So multiply everything by 600. Now you don't have to do this, right? Whatever you prefer, because you can simplify each term. VA over 100 is 0.01 VA. 12 over 100 is 0.12. VA over 60 gives you got a rounding error, and so 6 over 60, 10 over 40, VA over 40. There's only one rounding error in there. I'm not going to introduce that much of a rounding error to your answer. That would be appropriate to write everything as a decimal. But in any event, I find this way to be a bit easy. So 600 divided by 100 is 6. So that gives us 6 VA plus, remember, 600 over 100 is 6. So 6 times 12 gives us plus 72. No fractions, no decimals, right? And that's what makes this easy. Now 600 over 60 then is 10. So we got 10 VA. And 10 times negative 6, negative 60. Now 600 over 40 is 15. We have plus 15 VA. And we have 15 times negative 10, negative 150. And that sum then is equal to 0. So we have 6 VA, 10 VA, and 15 VA, 31 VA is equal to, bring my constants across the equal sign. I have 150, subtract 72 plus 60, because I got 3 constants to bring over there, right? And I could have done them in order, I suppose, but 72, negative 60, and negative 150. And so now that sum over there on that side is 150 subtract 72 and then plus 60. And if you do the math there, that gives me 138. So I'm left with now 31 VA is equal to 138. So VA is equal to 138 divided by 31, and it's in volts. And so no rounding now until the very final answer. And if you keep 3 significant figures, 4.45 volts for VA. Okay, so remember now that what we were really asked to find here was IX. IX is up, I3 is down. So that means that IX is equal to negative I3, because the direction is opposite. And remember that this was I3. So Vx then is equal to negative VA minus 10 over 40. So we'll keep our negative sign in front of the fraction, and we got 4.45 minus 10 over 40. And so see the double negative coming in here. We got negative, and 4.45 minus 10 is negative 5.55, I guess, right? Over 40. And so the double negative here makes it positive. And so Ix then is equal to 139 milliamps if I write it in milliamps and round to 3 significant digits. Now, let's go back to our circuit and think about the fact that we said Ix is up, the positive 10 agrees with up, the 12 agrees with up, the 6 probably don't overpower them, and so we'd agree, I think, that current was probably positive and going up through R3.